Hello, Harry. Hello, Hanman. Hello, everyone in the class. So if in case you're here for the first time, while I'm giving introductory word, please try to look online for MOBA X term and download and open. It's a free software, and then we'll go from there. Oh, okay. And then everyone just log into Photon server. Photon server is lowercase SSH space minus y space user add, and then continue in line Photon CHEM NDSU edu, all lowercase, and then it will ask password, and I'll approach just so. The subject that we are covering right now, subjects would of course will go much better if we spend like 4 or 5 weeks, but let's try to squeeze them in 3 weeks, where 1 is already done. So complete everything this week and next week, and then let's try to make presentations. So in 2 weeks from now, to leave at least some time for the projects. So today we will do 2 new things and 2 old things. Old things will be new things will be orbitals, but not in Gaussian, but in VASP, right? Another new thing will be absorption spectrum, which I do not have time to speak about at the lab, but during the lecture time I will provide additional background on what it is and how it is computed. 2 old things. Oh, and another new thing will be to redo all calculations on a remote high-performance cluster. This will be a little discomfortable because one would need to make several file transfers in a command line, but as soon as you get over it, it will be, the benefits will pay off. Is anyone in the waiting room? Hello, Sarah. Rizvi, you're here. You just dual. Okay. Hello. So cluster, and then when we log into cluster, we will redo density of states. The protocol will be the same as we did before, but we just need to make sure that we can do the same thing on other facility, that it is not specific for Photon, but it is available on other platforms. And at the end of the meeting, we need to, yes, we will do absorption spectrum. I was trying to do everything alone, and it took me 40 minutes. So with little stops and answering questions, it may run a little longer than 2 hours. Just but it would be really great if you can complete this program. So I will assist our
What was the password?
okay, and one more thing. Type your name. Okay. Okay, now you will be on the same page as everyone. Okay, so first thing we will do will be most spectacular and visually appealing. So it will be orbitals. Ideally, everyone should have the VMD software on the personal equipment. If you do, it will be great. Plus, if you don't, try to do it next time. As a backup plan, one can plot VASP orbitals on the Gauss View software as a plan B solution. But VMD is much more versatile and gives higher quality images. And later on, when we meet in a week, we will do molecular dynamics that is not possible to visualize in Gauss View, but it is a very nicely visualized in VMD. So basically, I'm going to follow the same protocol, the same script I did share with everyone. So if I'm typing something not clear, you can just use this as a reference. It's not prepared for easy digestion, but it is literally what I'm going to type today. And when we will be doing orbitals, we will return back to the simplest model of the titanium hydroxide. And here is one of the models, one of the orbitals, HOMO, which is expected to have a molecular orbital composed of p orbitals localized on oxygens, right? So in the next, whatever, 20, 30 minutes, we all should get this figure. And we already got same style of the figure on the based on Gaussian calculation, but now we are doing different software and different method. It will be not Hartree-Fock, but the DFT. Hello, Adam. Nice seeing you connected. Okay, so from now on, I'm going to make a little demonstration how to get this figure. So in the directory for the lab, I can do everything in U so that it will look as without preparation. Directory in U. And I need to, so you see, I have clear hands, no felony. Now, to this directory, I need to copy the coordinates from what we've had a couple of labs ago, whenever we did titanium hydroxide, or I can take it from whatever I was practicing recently. So cont car, copying here and renaming as a post car. Copy. Okay. So now I have one file postcar, more postcar. So 4 hydrogens, 4 oxygens, 1 titanium, and we have already computed the electronic structure, energies of orbitals, but now we need shapes of the orbitals. I'm also copying from the previous run the file podcar, which contains pseudo potentials, the K points. Now I do have 3 files, and there is one more file that I need to borrow from myself. The file which name is wavecar, and it is important to check that this file is not empty, so it has some content in it. To those of you who were practicing Gaussian, the wavecar is very similar by its function and content to the check file in Gaussian. So in addition to many things, it contains orbitals. So if this wavecar file for this system that we are considering is not available, one would need to redo it with a single point calculation. I anticipate that while visiting seats, there will be 1 or 2 human errors or something will not work. And highly likely, the most typical error is that this file is missing, or sometimes one may try to borrow it from different calculation, which will give a nonsense result. So it should be wavecar for the same geometry. And now when you look here, we are missing the in-car file, right? That we learned last week. So instead, last week, we were copying the in-car geometry optimization, right? Now we shouldn't do it. Instead of geometry optimization, we need to take another template. In-car PC, not for personal computer, but for partial charge density. We name it as an in-car in the current directory, and now we are all set. Well, not yet. In the previous run for the system, we were doing density of states, and we have a list of states, right? So from the file states that I hope you all have, we need the information about the range of energies for which we need the orbitals. So if you look into this file, we see that something interesting happening near the range where amount of electrons per orbital changes from 2 to 0. So this most interesting things happen maybe from -8, energy -8 occupied orbitals, and then to the energy maybe to -1. Make sense? So we just select a range near the gap. I just identified it as a human, and now I'm opening this template in car that is, you recognize, it looks very much different from what we had before. So the par d, L par d equals 2 means that it will be partial density, which is on WASP language, it is molecular orbitals. And if I'm going to the end of this file, here I need to specify EINT for energy interval. So I'm putting here from -8 to -1. It is the range of energies in which I want to explore all orbitals. for such small systems as we have right now, one can prepare numerically all orbitals at once. It's not a big deal, but if you go to systems with like 1,000 atoms and 10,000 orbitals, it will be a little too much. It will just consume all our disk space. So therefore, it's reasonable to look only on certain interval. So escape WQ. Another thing I can explore the NBA, which is not National Basketball Association. It is number of bands in the previous run for the same system. So it tells how many orbitals. It is either the end of the list of orbitals, or one can just ask from previous run how many orbitals were there. So n bands equals 21. Now I'm editing the incar once again, and I'm looking for this keyword. So in about line number 10, I see n bands, very big number, over 1,000. I need to replace it to 21. I'm replacing it, escape colon WQ, saving, and now I am typing the command to launch the computational chemistry software. So bin wasp photo. So and you see it shows the band. It is orbital in the language of WASP, number 11, 12, 21. So it shows orbitals, maybe not literally in the range where we asked, but close to this. 16 is Homo, 17 is woman. And after doing it, we see that there appear new files. Let me make a tour over seats and make sure that we all are on the same page. And then next stage will be visualization. So please try to arrive to the stage where these files are generated. And I will stop by and check how things are going. Let me type it. Okay. Just remember it and then erase. So it's the word we use to enter.
Wait, what? Oh, okay.
I just do not want to pronounce it because we are on the recorded line.
Okay.
Okay. And then, okay. Okay, everything's good. Okay. And now just launch.
Yeah, I missed the beginning part because I accidentally kicked myself out of the right directory, but I got back in.
It looks healthy, so it generates correct files.
Okay.
I've made a mistake and then I removed all the files.
It's fine. It's fine. PWD LS incar. Okay. Do you remember in which lab we explored titanium hydroxide?
Titanium hydroxide, I think I didn't make a folder for that, so it should be in the my names folder. So yeah, so
First lab on WASP. What was the number? 7 or 8?
7, I think.
Okay.
Let's see, 7.
No, it was still Gaussian. So you do not have lab 8?
I think I just like.
The files are not here. Too bad. Okay, let's just for sake of time.
Titanium hydroxide is right here.
No,
Is it
this is based on
the
Gaussian,
Gaussian?
and we need
Okay.
WASP. So you do. It looks like you. It looks like you don't have it. Let's just web 10. Just copy. No, it is. It doesn't feel happy. Pause.
I think we didn't edit the PowerPoint, right?
You should edit it while I was working here. Okay, I think it goes in the right direction. No, not a problem. You don't have wavecar. Or did you took these files? Yes. Let me check. Just- So you created a new. Okay, if you do it and you, then you need to do two steps things. Wait, just watch. So this is in car to create wavecar. Right now you do not have wavecar. Without it, it will not work. First you create to writing wave functions. It's now you see this. You see wavecar file is not. And now we can use the incar for the orbitals. Run it once again. So reading wave car was read successfully, and before it was not available. Yeah, my pleasure. So total number of orbitals in previous run for the system. Energy range. Why? Because we don't want all of them. Wave car, you do not have wave car. Why? Or you were doing titanium hydroxide in lab 8, right? Did you? Okay. But in also, let's do copy web 8. No. 8. What were you doing during the lab 8? So there is. Okay, let's look what is inside. There is nothing. It is bad. But we need lab 8.
Must be in 7.
7? Okay, let's look. No, it is Gaussian. We need, okay, let's look on the lab 8, 9. Maybe this is good. It's what? Oh yeah, sorry. Yeah. It's my error. Just a second. Okay, good. Okay. What's wrong? You didn't copy other files. Okay, let's try once again. Okay, yeah, it goes good. Oh, okay, I think it goes in the right direction. Can I see? Okay, yeah, great. Let me inspect and type. It's empty. So I've got this number in the following way. Grep number of bands, lab 9, out car. 35, then it should be different. Okay, and let's look states, maybe. So we, okay, from -8 to maybe a little further to like +1. It's bad. Random wave functions means it didn't work. So first you make run single point to generate wave car, and then you run generation of orbitals. I don't know why it didn't work from previous run, but after this is done, we need to run for orbitals. And if it doesn't work, we will just borrow files from my directory and make an attempt from there. Writing wave functions. Now copy in car into in car geometry. Copy in car per charge into in car. Okay, and now we run WASP. You see, wave car was read successfully, and now it shows only orbitals that you need. Okay, yeah, my pleasure. Okay, where's your lab 9? WASP was read successfully. Okay, I'm going to talk to those who are on the online. Oh, I see you guys are having healthy discussion. How do you do other kinds of calculation using WASP? Either remove something in the car, guide, WASP manual. Okay, good. So let me stop sharing and make everyone a co-host. And then we will make a virtual visits asking all online visitors to share their screen one by one. Okay, Hanmant, would you like to share a screen? No. Okay, let me ask your permission to remote control. So we need to copy to establish continuity from previous run to a new run. So it uses same service files as before, like same potential, same key points. And we also hoping that your previous run was successful. We need to inherit the wave car. Okay. Ooh, what is going on? So this exercise that we are doing right now is based on your success in your on success in your previous lab. So if something was not working last time, it will not work this time. Okay, looks reasonable. Let's try once again. Okay, so what is good? It tells reading wave car. The wave car was read successfully. It's a good sign. And now it converts, creates files for this orbitals. So in some sense, this rerunning VASP with different in-car is very similar to cube gen in the Gaussian. So we convert, in Gaussian, we were converting check files into cube files. Here we convert wavecar into part charges. So Hanuman, you can stop sharing. Oh. Is it like cats and dogs at Haley's camera and they're friends to each other?
Looks like.
That's great.
You think you have it.
It's an example of friendship. Okay, Haley, please share a screen and let your friends to type something on the keyboard. Okay, yeah, part charges are there. It was quite quick. Yeah, thank you. Sarah, would you like to share a screen?
Yes, sure.
Okay, excellent. Thank you. You can stop sharing. Anand is here in class. Umar is here in class. Lo, would you like to share screen? Okay, was great. You can stop sharing. Thank you. Adam and Rizvi is also here. Adam, would you like to share your screen? Okay, I think I'm going to ask you permission to type things on your screen. PWD. Make directory web number 10. File exists. Okay, let's look what are in those files, in those directories. ls and nothing. Okay, good. So let's copy. So we are taking heritage. Copy concar from previous lab into postcar of the new lab. And then we inherit the service, all service files except in-car. So key points, podcar, wavecar, hoping that it was correct. And just in case, because I'm lazy to read it here and there, I can copy outcar because I'm going to read one line from there. Now we are going to a new directory, change directory, and we are copying the in-car from the template. PC space in-car. Grep National Basketball Association outcar. Number of bands 21. VI in-car. So number of bands should be same as in previous run, 21. And we already know from other class participants that reasonable range for orbitals is from -8 to about 0 to -1. Escape, column WQ. And now just run wasp bin wasp dash photo. So you see it shows reading wavecar. Wavecar was read successfully. It is a really great line that helps to identify that we are doing good. And here you have orbitals. Make sense? Any questions? If there are no questions, you can stop sharing. And I think I do not hear anyone except myself which sounds a little selfish. Let's check speakers. Anyone, maybe Adam, just try to say something. Oh, okay, your microphone is broken. Haley, would you like to try your microphone?
Hello.
Microphone, speaker number 1 doesn't work. Testing speaker number 2. Try.
Hello.
Doesn't work. Testing speaker number 3.
Hello.
Doesn't work. Testing speaker number 4.
Hello.
No. Please try once again.
Hello.
Oh, yes. Hello. Very happy to hear you and very happy that system is working. So I will be not the only person who is speaking. Okay. Thank you for assistance. I resume screen sharing and we'll go further. So those of you who did install VMD on your personal computers, please download all ParCharge files and postcar file to your local computers. I'm going to show what to do if you do not have VMD, if you how to plot these files using Gauss view. So in order to do so, one can convert WASP-specific files for orbitals. By the way, we can look inside more ParCharge 16. Okay, so it reproduces the coordinate, so fractional coordinate size of the cell. Then it gives the number of grid points along X, Y, and Z, and then there will be just several kilobytes or megabytes of the data. So that each data tells probability density at certain point that we will need to plot. So there is a script that converts ParCharge into cube file. AT tools. Charge CHG2 cube. And then one gives the name of the file, ParCharge 16. Okay. So it asks which type of the file. So it can convert 3 types of the file. I'm answering number 3, which means ParCharge. Now element types. So before I was looking on this postcar or ParCharge files. Let me script here. So it tells that my elements are HOT, hydrogen, oxygen, titanium. And if I look in the periodic table, I can put their numbers. So hydrogen is 1, oxygen is 8, titanium is 22. Then it is done. LS minus OT head. Oh, it shouldn't use uppercase. LS minus OT head. No. Once again, LS minus LT vertical line head. Okay, I do have a new file, so it's ParCharge all k.cube. And if I do not have VMD, I can visualize it using Gauss view. So I'm just typing G view exe. That should start our favorite Gauss view code. Closing tips, going to main control window and trying to open file, open, selecting file type cube files. And here is this cube file that was converted from WASP to Gaussian format. Opening, so first it shows only the model. And I'm going to do the same things as we were doing in previous labs. Results, surfaces, contours, surface action, new surface. So you see it, it doesn't show positive and negative because it's not the wave function's probability, is wave function squared. But you see it shows this p-type dumbbell shapes on each oxygen, right? Which goes very much along to what we had in Gaussian calculations. So if you do not have VMD, just repeat this exercise, and I will switch. I will share screen from another piece of software and make demonstration on VMD, and then I will make a tour and will help to whatever software you are using. So, and if some of the codes, some of the commands are needed, please look onto the either body of the email or Word file that I sent to everyone. It has literally all commands that I'm typing right now. Okay, stop sharing. I'm going to another station and sharing screen. Sharing screen. VMD. So here, this thing is already done, right? But I'm going to create it anew. So this will be in VMD two-stage process. So first one needs to, I will be cheating a little bit to speed up, but first, in Gaussian, we do have molecule and the isosurface coming almost simultaneously. In VASP, in VMD, one needs first load the postcard to have the molecule. Then select type of the VASP postcard, and then click load. And then one is getting the molecule. And then on the top of this, one needs to type, click load new molecule, and select, maybe and select the orbital per charge file. So I'm clicking on per charge. Well, 16, we already saw it. Let me select maybe instead of HOMO, select LUMO, which is expected to be on titanium rather than oxygen. So selecting, then identifying what is the type of the file. So VASP per charge density spin up plus down, load, and then it shows this d orbital. Sometimes you will see nothing by making this click. So I did inherit the settings from previous run. This happens because here is the isosurface value. Typically, by default, it goes to points, and points show nothing. They are very scattered and not seen. So wireframe is old-fashioned for very slow computers, and solid surface is a little bit more modern. So you select solid surface, then you pull this bar for selecting value of ISO value. So small ISO value, large balloons, small, large ISO value, small balloons, same as we did in Gaussian. And there is another way to make it transparent, so that if there are several orbitals, you can see through. There are ways to make it to look more beautiful and nicer. It's just not our goal at this point, but I prefer orthographic. One can go to colors and make it white background. And then this figure is a little bit more publishable if we need orbitals of this simple molecule. One can mouse, scale, so one can enlarge. There are many things to do, but as soon as you get this figure, you are good. Okay, I'm going to make tours first, those who sit in the class, and then those who are online.
I tried to do, I went in to enter these and it said that it does not match the number of. Right.
I'm confident in these numbers. Okay, well, let's just do another exercise, copy the template file, and because time is very limited. So this here. Okay. Cube. Now go to main panel, results, surfaces, contours, surface action, new surface. So it is already there. Okay. Okay, let me just show it quicker. Okay, yes, now type of the file. Change. Okay, load, and now we go to the main window and go to representations. Representations, replace points to solid surface, and then you can play with this.
Okay.
Okay, make it transparent.
Thank you.
My pleasure. Okay, that's great. it's I thought okay. Place points to solid surface. Play with the ISO value, and one can make it transparent, right? Oh, I love this software. One can do other things. So display white. Okay, and the molecule, it looks much better if either CPK or if it is something half broken, one can do dynamic bonds, but okay. So, oh, okay, you have VMD. Did you download the file? Postcar and all port charges. Okay, good. Now find this directory. Okay, good. So starting with postcar, where it is? Okay, open. Type was post mode. Now there should be here it is, and one can make it look better. Instead of lines, do CPK. Okay, and now we need to read the orbital rows. Some orbitals. Let's do another one. 18. Open. The file type. Per charge. Load. See, it's very ugly dots, points, but if you replace points to a solid surface, it looks really great. And then you can play with this with the surface view and make it transparent. Okay, did you download it? Not yet. Did you look in Gauss view? Okay. Okay. Okay, but so let's make them beautiful presentations. Select lines. CPK is better. Let's select the charge. Right now it shows points, which are very old-fashioned and ugly. I can do mesh, like in old movies, and the best one is solid surface. and one can play with ISO value. Okay, it happens, but right now the task was just to plot orbitals. Do you have VMD? Did you try? So if you have, well, we will be doing other things. Try to download this part charges to your computer and try to open them in VMD. PostCar and any of the part charge files. Excellent. Did you try VMD? Okay. Okay, let's interact with those who are online. So I stop sharing here. Hanan, would you like to share screen? Okay, great. Do you know how to make it transparent? No. Graphics, representations. No. Representations. Now select model per charge. Yes. And replace opaque material to transparent. Okay. Yeah. Very good. You can stop sharing. Thank you. Haley, would you like to share screen? Okay.
How do you make the ball and stick representation?
Let me ask you permission for mode control. It will be just a little quicker. So graphics, representations. Now select molecule. It thinks that it's different object, postcard. Clicking on the postcard. And now it shows drawing method lines. So there are other things. The quickest way is CPK, which is better. And there is an even better way that helps when we look on chemical reactions. The dynamic bonds, we can make a little smaller cylinders and a little bigger threshold. Okay, and create wrap to add balls as van der Waals and make them a little smaller radius. Do you like it better?
Much better.
Oh, okay, thank you. You can stop sharing. Sarah, would you like to share screen?
I'm not able to copy to my desktop. I don't know what's wrong.
Okay, so are you going to use? Let me see what you're doing.
So here is my, on the right, here is where I am. I have all the files and this is my directory. And here I'm using this command to copy to where I am, but doesn't work.
Let me request
Sure.
request remote control. And yes, let me look symbol by symbol. Photon chem and DC reduce scratch chem 10. I think capitalize L.
No, it's not. Because on the right, the terminal on the right has my path, which is
Let me see. Um, let me try several things.
okay.
SSH. Okay, it recognized it. Good. Let me just retype SCP. Scratch 001. CHEM 476. CHEM676. Everything to here.
I don't know what's going on.
Huh? Do you have other ways to
It used to work. Like I use this like for my homework and to scoping, but I don't know what's going on now. Oh, okay.
so I just type bash, a little different Unix shell. Okay. Now I noticed you do have.
I have VMDS.
Yeah, please bring it up. I do not see everything on my screen.
Yeah, let me try to open it for you.
Yeah, just open VMD, bring its main panel. Okay. Let's just. So please
okay.
the directory where you. Okay, select postcard. Okay. Determine file type. Yeah, click and select postcard. Okay, load. Now we should see the molecule which is represented as a wireframe, which is a little substandard, but we can go to representations and replace it to CPK. And just a smaller orthographic colors.
Oh, I'm sorry. I'm so sorry.
And now the second part, we need to load new molecule and select the orbital. Let's select some other which no one did. Select an orbital, file type. Just please scroll down and identify this WASP par charge.
Okay.
Lower at the very alphabetical. Yeah, WASP. No,
Charge.
Par charge. Two more up. No.
Oh.
Yeah, this one. Click. Load.
Spin down. Oh, okay.
Load. And now we see nothing, which
Yep.
we shouldn't panic. We shouldn't
Okay.
panic. The draw style is points, and we should replace it to solid surface. Now one can play with ISO surfaces
Mhm.
and make it transparent.
Nice. Yeah.
Okay. Color ID and make it whatever you want. Okay, you can stop sharing.
Thank you, Professor.
Yeah, thank you. Anand is here in class. Umar is here. Lola, would you like to share a screen? Hello, Lola. Would you like to share screen? Would you like to share screen one? Okay. Okay, good. Did you try to use VMD or you're not interested?
I can download VMD, not like I wasn't interested.
Okay. Well, please help each other and make consultation to each other how to download and make it running. I'm just not having time to do it in class, but you see that half of the class was able to do so. Just try to help each other. So we can stop sharing.
Thank you.
Thank you. Adam, would you like to share a screen? Adam, thank you for sharing. Okay. So are you sharing only mobile external window or the whole display? Oh, okay. Maybe open, file open. Open, select file type cube. Yes, yes. And just put it a little, yes. Results, surface contours, surface action, new surface. Okay. Looks okay to me. Yeah. Thank you. You can stop sharing. Okay, now I'm going back to sharing screen. And we spent 1 hour and 20 minutes and we did about a half. So prepare your internal strengths. Now we are going to do something painful. It will be not challenging to your intelligence. It will be just challenging to your, how to say, patience and concentration. So we are going to make a chain-wise connection through, so to say, proxy. We're going to connect to remote high-performance computer cluster. Then we are going to forward our files that we were working with today there, rerun WASP on the remote server, redo density of states as you did a week ago, and create density of states image, same as you did in homework. So it's basic. Last week you were able to do it. The only thing that we will do it on a different computer, and before we had only one leg of file transfer from your local computer to Photon and then back from Photon to your local computer for visualization. Now we have two legs, like airfare with two connections, right? So transfer file to Photon and then from Photon to remote server. Then after generating results, download back from remote server to Photon and back to your local computer. This is something that I hate, but it's best thing we can do to the remote computer will be so quick that it will pay off any efforts. So it has like 50,000 CPUs and it is within 10 first 10 supercomputers of the world. Okay. And again, if you do not like and don't recognize what I'm typing, I will be just repeating what I sent in this Word file and in the body of the email. Yeah. No, it's low performance. It's not desktop. It is like server with 64 CPUs, but it's like our desktop PCs are little towers, and Photon is just a thicker tower with a little better ventilation and a little better disk space. So it's not a high performance; it's low performance. Okay. So PWD. Maybe I would benefit from opening a second window. It's not necessary, but I feel it more comfortable. In the new window, I will log into Photon once again. Photon. Oh, I cannot type better. Okay, and now there is a command that brings me from Photon to remote server. The command is too long for my limited intelligence. Therefore, I created a little cheat sheet for myself. So more being advice nurse. So I'm just copy pasting this SSH line. And after I type it, it brings me to where I have to be. So let me pause, resume recording. Now, there, same as on the Photon, the home directory has very limited amount of memory or disk space. I have another cheat sheet which shows the directory with much more space. And there I'm just going CD to this area. And I'm not trying to type ls because there is a lot of files created through years, but I'm going to cd CHEM676 2022. Okay. PWD. I can go right away to this directory. So let me share it in the chat line. Okay. And there, right now, there is only one subdirectory for myself that I did while preparing to this lab. But please type, same as you were doing when starting this class, make directory and then type your name as you want to identify yourself. Like whatever you want to be referred to. And then hit enter. Okay, I think half of the class already did it. Now, change directory to your directory, not to mine. I'm typing CD Dmitry, but you can type CD and your name. There, I also have created make directory lab 10, and then I'm there. So I'm going to create directory, make directory new, so that you see it empty, and I'm just showing things as we go. So by now, you are on a remote computer. You can learn in which directory you are. So by policy of this remote computer, you should transfer files by staying in this computer. So instead of uploading to this computer from Photon, you should download your files from your directory to here. So let me explain what I will be doing just by an example. So I'm clicking on the different tab where I'm on the Photon. Here I'm copying the whole directory, copy, and then I'm going back to this new supercomputer. And here I'm typing SCP, same as if I would be on the personal computer, user Photon CHEM676 colon, and then I'm pasting the path to my directory. So I'm pasting path to my directory. You should use path to your personal directories, right? And then in the future, I promise to myself to save disk space, but now I want to save time and just transferring everything. Start period point, which is not a good practice because wave cars are too big, but and hitting enter. And then I'm typing password for the Photon server. And then it just transfers everything from Photon to this supercomputer. So let me share this template, but by looking on it, copy, chat, paste. Plan to use your own pathways. Now I can type ls. There is something, and although there are pre-made files, I want to rerun all steps. I want to just run from scratch because there could be different versions of the software. So maybe I will do the following. I will neglect the things, make directory new2, and I will copy there only minimal amount of information. So copy the font car, rename it as a postcar, copy a points, and copy port car for potentials. So, and then I'm going to this new directory, cd new. So right now there are only 3 files, right? So I'm thrown back a week ago input files, and I want to find orbitals, find energies of orbitals, and create density of states plot. So there are similar templates in a similar type of directory. So copy bin in car geometry optimization period underscore in car. Just in case I look inside. So NSW equals 0 means no optimization, single point. If I want to optimize geometry, I can replace this number to something bigger. Let me copy this line just in case. Copy into chat line, paste. Okay. Now, close this, click here. Now I do have 4 input files which should be sufficient to run WASP. But on remote, on high performance supercomputers, typically there are like from 10 to several thousand users. And if anyone runs jobs on a front node, it's very non-friendly, at least, and it is punished by system administrators at most. So on Photon, we were running WASP directly in a command line, which is okay for first steps education, but for high performance, for high productivity is very bad. So instead, the clusters are arranged as a front node or several front nodes, and then many compute nodes. And there is a so-called job scheduler that distributes our jobs over compute nodes. So we need to make, and I think Amaro or Sarah were teaching us to do it with Gaussian. Sarah, did you teach us how to use job scheduler on CCast?
Not me.
I think you did.
Oh
on,
yeah, yeah, WASP, yeah.
On the lecture 17.
Yeah,
Okay.
gotcha.
So
Yeah.
now we will do similar things if you were present at her presentation or watching the recordings, but we will do it on the different things, so different facility. So in addition to input files, we need one more file that will help us to communicate with the scheduler, okay? And this file is also available as a template. So copy bin q debug.sh period. So let me copy this command as well. Copy, paste. Okay, now I do have 5 files. Just for curiosity, I can look inside this debug cube. So it is a different job scheduler. I think the one on CCast is PBS, and this is different name, but it is, and the scheduler script is much shorter. Here, the debug queue is means that it will go into the, it will be running almost instantaneously, but it is limited to short time. Later on, if we need longer jobs, we can replace the word debug into regular, and then we can use much more resources, but we will need to wait like a couple of days in the queue. And here it just tells that we are going to use the WASP code. We are going to use single node and 64 processors. And we are going to use gamma point, which means no k-point distribution, which agrees with our k-point file. So I believe the command is sbatch, and then this name of the script. So after I type it, it gives the number of the job, and I can type SQS grep and then this number, and it tells, okay, PDs means it is pending, so we need to wait. But depending on the load on the cluster, it will be instantaneously, or one could wait no longer than half an hour. And if I want to check this command again and again, I just type watch. So it will change the letter PD to letter R when it will be time for this job to run. Let's check. Okay, I think a couple of there are a few jobs in the queue, but they will purge through, since it is allowed only for 30 minutes, it will be quickly available. So I'm going to visit all seats and make sure that you submit your jobs. And as I'm making this visit, they will be completed. So it may look a little annoying because when you were running jobs on the photon, they were starting instantaneously, but this running jobs on the remote facility is the only way to deal with big models. If you have some heavy scientific or engineering applications with system with more than 50 atoms, like 100, 200,000, photon server or CCAST cluster will be just failing to do them. So one needs to wait a little, but it will give benefits. Okay, I will visit everyone on seats and then those who are remotely.
I just couldn't get the password in. Like I tried to enter that in. Are there any spaces there? Or
No.
No.
Yes. Sorry.
Oh, and there's light in there.
It's the same word, but in opposite direction. I apologize. I just remembered on the tips on fingers.
That's all.
It's just tired of waiting. Let's do it once again.
So then,
Okay, let me type it. It will be just quicker. So we need post continue. We need key points continue. We need pod car, and that's it. Then we go to this directory. We copy template. Space and car, and we copy.
Excuse me, could we submit a job?
Huh?
Should we submit the job? Should we?
Yes.
Okay.
And the debug queue may not accept more than 5, then you can submit to regular. Just replace the word debug to regular and it will accept more.
Okay, thank you.
Okay. Yeah, let's we just can. Basically, the escape. So it doesn't want to take it, right? And if you replace the word debug into the word regular, it is there. Grep, then please copy paste. So it's pending, and if it will be done during the time of the web viewers output of this. If it is not, I will just share pre-made files so that we do not waste time.
Okay. Sounds good.
I think I've submitted the job.
No. The command to submit is sbatch.
Oh.
SQS is just watch what is submitted.
Okay.
And I think right now there are too many. It doesn't take. So if it runs only 2 at the same time and keeps only 5 because it is high priority. But if we change the word debug into a little longer in the queue, but it will go into the it will be submitted. So S batch,
Okay.
and then there is your
The job.
yeah SQS grep, and then copy this 56601 9. Well, just check it from time to time. If it will be completed by the time the class will use results that you generate here. If it doesn't, I will just share templates pre-made on my, so that we do not waste time.
All right. Sounds good.
Okay. Okay. Let me. Yes, this is your job. Okay. Okay. Your number, right? No. But it's still pending, right? Because there are so there are two jobs from this account currently running. They use 24 minutes. As soon as they are done, next 2 jobs, and then your job will come. Okay. Okay. Okay, so SBatch didn't work, right? Okay, let's do the following trick. Replace the word debug to the word regular. Skip colon WQ. Then repeat. SBatch. Now it is submitted. And you can check and then copy paste this. So it's pending, but this time it will change PD to a run. And then this job is so simple, it will run in like 40 seconds. Yeah, thank you. So you can check it from time to time. And right now it's PD. When it will be running, it will change letter R, and when it is done, it will show nothing. Right now, there are just 5 files. As soon as it is done, it will be like 20 files. Okay. VI, this debug, VI space debug .sh. Replace the word debug to the word regular. No, just do it as you typically edit files. It doesn't recognize, you need to use arrows. Type regular. And then
Excuse me, Professor.
enter. Sarah, I'm hearing you. I will be very soon to those who are online. Now SBatch debug, space debug .sh. And then we can check how the job is progressing by SQS. SQS, vertical line, vertical line, vertical line, vertical line, grep, and then copy paste this number. So right now it shows PD. When it is done, when it is running, it will be R, but it will be like few seconds. And then in arrow up, type arrow up, enter. After the job is done, on this, in response to this command, it will show nothing. And on the command ls, there will be like 20 new files. VIG. So right now it shows PD, which means pending, and you can just repeat it. After some time, it will show R, and then it will after the job is done, you type this command, and it will show nothing. And right now you have like 5 files. After the job is done, it will be like 20 files. Okay. Okay, you're lucky. It is submitted. SQS, grep, and then copy paste this number 56602. So it is pending, but after some time it will show to the letter R, and later on it will disappear. Right now, if you type ls, there are only 5 files, but as when job is done, it will be like 20 something files. You can just check from time to time and see the progress. So you see here on the screen, CG means job is done. And as soon as you see on this screen that there are less than 5, right now there is a window. Someone can try to submit the job in debug queue. See, there are 4 jobs. Very soon it will be 3. So maybe 2 of us can submit. Okay. This job will be done. Now three persons can submit in the debug queue instead of regular. You see, these jobs, oh, one more is ready. So 4 people you'll be able to submit. Now this one is running and it is done. This one is running, 53 seconds, 55 seconds, 57 seconds, done. So CG, it means it is finishing. Now 5 people can submit into the debug queue. So just use your chance. I'm going to stop sharing and ask those who are online to share their screens. Hemant, would you like to share a screen?
I don't know, something happened. I am unable to type anything.
Okay, let me request the control. And check in your other directories. New lab 10.
Lactate.
Are you trying to run here in this directory? Yes?
Yes.
Let's look in your previous. So, but I do not see S batch command. So to grab, did you type the S batch command any time before?
No.
No, you need to type it. So S batch debug. Okay, your job is in the queue. And you type SQS grep and you copy paste this number. So your job is already running, and if you type ls, you see there are more files. If you type this SQS, it's still, oh, it is already done in 14 seconds. So it's minus LT, and one can check if the job is complete by tail out car. So if it, no, it is still running. Maybe there was an error. If some files were not correct, then it was, yeah, your postcard is empty. I don't know how it happened, but empty postcard is not good. So we need to fix the error. And if you look this swarm out, it tells it will tell you what the most error. So it tells that there are problems with postcar file, and then it just terminating the job because it was empty. So ls postcar in there. Oh. Okay, in the new, so you need this one. So copy your postcard from here into new 2. So I just want to make a little disclaimer. Some of you just repeating what I'm doing. I was creating subdirectory new because in the subdirectory lab 10, I already practiced what we need to do today. And it will be not helpful and not educational if I just run over in the same directory. If you have your lab 10 directory empty, you do not need to create this new subdirectory named new. So I just was trying to play fair game and not using pre-made files in the same directory, show how they developing. Okay, more postcard. Okay, it's not empty. Now let's go to this new 2. More key points, more pod card. Okay, more in car. Okay, and now more debug. Okay, s batch debug sh. And then sqs grep copy paste this number. The job is running. More OS z car. Not, it's empty. No, it's not empty. So you can watch as OZ car file is increasing. It shows the iterations of electronic structure, and it is a self-consistency cycle, same as in Hartree-Fock, and in DFT it also available. When you run, oh, okay, it is done. When you run Waspin command line on Fortran, you also see this list of electronic iterations. Now I type SQS and number of job, and it's still running, but it will be done very soon. Like it takes less than a minute. CG means it's about done. And now it is done. Now I type tail out car. It gives this report of spent time, and I can look the whole out car. It will at some point in the middle it will have the list of orbitals. Yeah, so this table of orbitals you need to copy paste into the file named states. Which we need for our next exercise. So the I states I paste escape colon WQ. So Hanman, you can stop sharing. We need to check this.
Thank you.
Haley, would you like to share screen? Haley, would you like to share screen? Okay. let me request the control. And so it looks like you were creating orbitals. And we do want to recalculate the electronic structure. Let's make, oh, okay, let's go to new and see what is there. Okay. It has slurm. Let's look for more outcar. Oh, postcar is 0, is empty. So it will be also an error, more outcar, and it will show some error message. Yeah. Okay. So in your lab 10 subdirectory, you have, no, just this way. Yes. You likely have the healthy postcar. No. And what about contcar? No.
You have to put a space after more.
What?
You need a space after the more.
Oh, okay. Yeah, thank you. Can you type it instead of me? Maybe it will follow your keyboard better. Okay, it is good. Yeah, thank you. So, postcar is here. Postcar is here. Grep PW postcar. HOT. What else? In car is reasonable. Okay. More debug. But by some reason, let's check once again. More. Okay, let's just rerun and see what happens. As batch, debug, SQS, grep, and then okay, it's already running. Postcar, it tells postcar, so it tells there is postcar is empty. It doesn't recognize postcar. Let's check once again. More postcar. Okay, let's copy from lab 10 into here. More postcar. Okay, here it is available. Now let's resubmit the job. Dispatch debug. Okay, it is running. Okay, now it goes in the healthy cycle, and it is almost done. Okay, it is done. So we were trying to start from scratch and redo electronic structure. Does it make sense? Haley?
Yes, thank you.
Okay. So the next thing we are going to do is to explore car. Identify the spot where it has the list of orbitals. And copy paste the segment in the vicinity of Honolulu into the file named states. Copy Q I states I paste escape WQ. Okay, you can stop sharing. Sarah, would you like to share screen?
Yes.
Okay.
But my out card looks like this only. I don't know why.
Yeah, let me request control and inspect something.
Yep.
Yeah, thank you. So postcard is non-zero. K points are unavailable. Right? So we need K points file. Let's copy it from template. Copy bin points. Okay.
So that means it didn't copy when I was copying the folder.
I don't know. I don't know how it happened, but podcar is also unavailable. Let's check. Maybe you did a
Yeah, I can't
you
see.
don't see podcar.
So let me grab it quickly. Okay.
Let's recreate. Let's recreate it, and it will be a little demonstration, and it's on the recording. So for the postcar, we need the hydrogen, oxygen, titanium, and location of the potentials is slightly different on this cluster. So module show WASP. The pseudo potentials are located in this directory. So cut PBE PBE. Now it will ask, do I no? Now it hydrogen pot car bigger pot car once. Next one is oxygen. And next one is titanium. Titanium. So you have key points. You have grep PAW pod car. You have I typed wrongly. We have pod car. We have in car, right? We have debug. Okay, and now we can as batch debug sh. Enter. SQS grep SQS 566 26 36.
There is 0.
It is either done or it has an error. So tail out car. Maybe I typed it wrongly.
Yeah, there is 0.
But it looks like almost done.
Yeah, it's running. I guess you typed the name in the number of the job.
Yeah, okay, but
okay.
now your job is done and
Mhm.
more out car. So we scroll through and identify the spot with orbitals near the gap and copy, quit, VI states, I paste, GG, escape, WQ. So you can stop sharing and we will be quickly working with this file after we're done with everyone.
Thank you.
Adam, would you like to share a screen? Okay. More states. Perfect, perfect. Very efficient. Thank you. You can stop sharing screen. Okay, now I will be sharing screen on my side. So please check that everyone has this outcar files. If your job is not done, just copy paste it from like my subdirectory because we need to go quicker. Please raise hands who has outcar done. Okay, yeah. Now just manually scroll through the outcar file and closer to the yeah, I think there are some errors in on my side, so which I have to quickly fix. Okay, I think it is done on my side. More. So scroll until you see this list of orbitals. It will be like 90% from the beginning to the end. And just copy the segment close to where we have transitioned from occupied to unoccupied orbitals. Copy, letter Q to quit, and then VI states uppercase, then type letter I for insert, and then paste for placing it there. If it ends below the line, I type escape DD so that there will be no empty line at the end, and then escape column WQ so that I have file states. States. So we are, I understand we are over time. If someone has scheduled events, feel free to leave, but I'll stay here and continue because we need to complete logical step. So we're going to repeat absolutely the same things as we did on Photon, but I want everyone to be sure that we can do it on this remote computer. So there is list of orbitals is discrete, and we need continuous density of states, which is a average characteristics, which has bigger values at the region where there are quantum states, and it is 0 in the region when there are no quantum states, right? So the script that does it is address DOS norm. And if I run it, it starts asking several questions. So before running the script, I need to learn a little bit about this system. So I need to make WC states to learn how many lines in this file. I need to grab number of ions in the outcar, 9, I knew it. I need to learn number of electrons in the outcar, 32. And I need to learn what is the Fermi energy from the outcar. So after it is done, I can run this script, and just, it's a little interview, a little dialogue. So number of states. So it's basically number of lines in my file. Depending on how you were creating this file, the number will be different. So in my case, 25. Minimal energy, maximal energy. So it is a range of energies where I want to create my density of states. I can try making it from -10 to 0. Fermi energy, I copy paste this E Fermi. Alpha plus beta, I copy pasted this number here. Enter. Width of each line, it prompts some value. Magnitude 1, number of atoms 9, number of electrons 32, gap of bulk 3. DOS Fermi is written. So T head. So let me just copy paste the path to this command in chat line. So after so it creates this file DOS Fermi, and then we are converting it into graphical file by GNU plot, GNU bin, GNU prog underscore DOS1. Then with my if I look for new files, it has this dos.ps. Copy, chat line, paste. So just in case of curiosity, here is the content of this script. So it just plots file DOS Fermi with line 3 as energy, line 4 as density of states. And then .ps is obsolete format. We need to convert it to PDF. PS to PDF, FWR, right? DOS.ps. After this command, there is a PDF file that I need to transfer from remote cluster to Photon. So if I type arrow up many times, I'll probably will get no, it's not. Okay, then I design the command over again. So I need to SCP everything that ends as PDF, and then to the user at photonchem.edu column, and then I look into the tab where I was okay. I'm copying the directory where I want this results to be on the photon, and I paste it here, and then typing the password. Just in case, let me copy paste this command, but it will be different for each individual user. So it's just a template. And after I transfer, I look in the directory on NERSC, and this file is here. For bringing this file to display, I can either use SCP once again or identify the directory where we are working on this little tab. So CHEM676 Dmitry lab 10 NERSC DOS PDF. So those are occupied orbitals near -6.9. Those are unoccupied, like those are on oxygen, those are on titanium, and very interesting. Here is degenerate like 2, then there is a splitting, and there are 3 orbitals. This, those of you who take inorganic chemistry may recognize tetrahedral splitting, like 2 plus 3. Total d orbitals are degenerate in vacuum, and in the environment of ligands, they split on groups of 2 and 3. So please try to repeat it. Let me know if I need to bring maybe this line here, and I'll make a quick tour, making sure that everyone can repeat it. Just. Can scroll up. Stop. So just copy paste this segment. Enough.
Okay.
Whatever. Yeah.
And then this goes in states, right?
Yeah. Type vi space I. Go to the last line. Type escape DD. Denver DD. Now escape. Column WQ. Okay. WC space states. Enter. Grep space NIO uppercase, number of ions uppercase NIO. All 3 uppercase. NIO space outcar. Enter. Grep space NELE uppercase, number of electrons. Number of electrons, space outcar. Enter. So 32 electrons. Grep space lowercase Fermi, FER, space uppercase outcar. Enter. Okay, and now tilde/bin, wavy line tilde, shift tilde slash bin slash uppercase dress underscore DOS underscore norm. Enter. Norm without a. Enter.
Norm,
Number of states 43. It is what you've got.
Oh, yeah.
Enter. Minimal energy -10. Enter. Maximum energy 0. Enter. Fermi energy, whatever you've got here, -6.7. And enter. Alpha plus beta -0.5. Enter. Width of each line 0.005, whatever. Magnitude 1. Number of atoms 9. Enter. Number of electrons 32. Enter. Gap 3. Enter. So this DOS Fermi file is written. Now GNU plot space tilde slash bin slash GNU prog og underscore uppercase DOS1. Enter. PS lowercase ps number 2 PDF WR. Once again, space uppercase DOS dot uppercase dot PS.
Dot
PS. Enter. Now, if we look, there is PDF file, right? And we need to transfer it to your screen. So copy, go to a different tab,
Oh, no.
SCP space star dot PDF space KILIN at photon.ndsu.edu chem before ndsu chem.ndsu.edu colon paste slash enter. Okay, and there are typically
It's we need to like
can you okay. So go to the same directory. So first we go to root, right? Slash, and then identify the Scratch 001. This one, this one, this one, this one. Look similar. to what we had.
Awesome.
Excellent. Perfect. Thank you. Great. Did you get it?
Yeah.
Okay. Okay. Did you get it? Okay. Let me type something. Um, okay. Uh, wait. Where's the nurse? Okay. Okay. Good. It's empty. Mm-mm. No. There is no postcard. Okay. Good. Oh, okay. 28. Okay. Huh? Shift. Yes. Okay. Did you get the DOS? What? You didn't create this file. So copy VI states I. Once again. Copy. Paste. So can you please paste? Okay. Okay. Excellent. Thank you. Amara, thank you. I see it. Okay, let's quickly go over those who are online and who is still here on the connection. Hemant, would you like to share screen? Okay, thank you. You can stop sharing. Haley, would you like to share screen? Perfect. Thank you. You can stop sharing. Sarah, would you like to share screen? Excellent. Thank you. You can stop sharing. Adam, would you like to share screen? Okay, yeah, keep going, -10, enter. Zero, enter. -7, enter. -1, enter. 0.005, enter. 1, enter. 9, enter. 32, enter. 3, enter. Okay. Let me request remote control and double check what is going on. More states. Okay, there is an empty line at the bottom. Many computer programs are getting upset if they see it. So escape DD, escape WQ. So DD means delete. WC states 20. Let's redo this. Number of states 20. Minimal -10, enter. Maximal 0, -7, -1, 0.005, 1, 9 atoms, 32 electrons, gap 3. Okay, done. GNU plot space bin GNU prog underscore DOS1, enter, PS to PDFWR DOS dot PS. Let's manage T. So we have DOS.pdf. Now we look on the other tab. PWD. Yes, you already made this preliminary step. Thank you. Copy. SCP, anything that ends with PDF, into photon. CHEM NDSU and DSCU.edu colon enter. Okay. It is here, and I need your assistance in. Oh, okay, I've got it myself. Bringing up this browsing file browser. So we're going to scratch 001, CHEM676, 676 here 22, lab 10, NERSC, DOS. Okay, I think you're good. So yes, thank you for demonstrating. I was intending to make another skill of absorption spectra. We all should finish our day. So anyone is welcome to disconnect and depart. I just quickly do it so that it will be at the end of the recording. And when we meet on next Wednesday, we'll start from it. But just in case, for those who are really curious, I will do a quick demonstration. But I'm not holding anyone. Everyone is welcome to disconnect. Okay, so on the query, I am copying the states into energy underscore pop for energies and populations. I'm looking onto this file and looking the first orbit. It starts with 9, ends with 33. Making a file input underscore overlap. First is 9, second is 33, and then 1 is just a service number, WQ. Now I do not count on my memory. So more score underscore bin device dot spectrum. And basically I am copy pasting all these files one by one. First line is changing the libraries and default Fortran compiler. Second line, I'm copying the executables to make spectra into here, whatever they are. Third one, I'm running the script that reads wave car and creates oscillator strings. This is a big deal, and we are co-authors, Professor Svetlana Kilina and myself. We wrote this code in 2004 and were very happy and using it through the career. Okay, after this is done, there is a file oscillator strings, and let me bring up this when there are two more lines. So we move oscillator strings oscillator all, because right now we show all transitions, including from occupied to occupied and from occupied to unoccupied. And this last line creates only transitions from ground state to excited state. Now we have this os strings file that has the third column is oscillator strings, fourth column is energy, here is source orbital, here is a target orbital. There is a script that converts it into the absorption spectra. WC os strings, and the script is bin spectrum improved 3. Number of transitions 136. Minimal, okay, from 0.5 I would go up to 10 because it's UV. Point of each line, thermal broadening last time. Number of HOMO, I don't remember what it is. I think it is 16, right? When we were doing orbitals. Okay, ls minus OT. So it shows spectrum file, and then one can plot it either in Excel origin or by GNU plot. GNU plot. Score SPE, spectrum 1. After it, there is a SP1PS, PS to PDF, WR SP1. So we convert it into PDF, and now we can transfer this file to Fortran same way as we did before. Just arrow up until I see this transfer command, typing the password, and then going into the correct directory, scratch001, year 22, directory, web 10, so there is a SP1. So this is a very important thing. Just by computing spectra like this, one can do a real science, and it will be publishable. It shows we scan transition energy and we see response at which transition energy the molecule is able to absorb light. This is the simplest way to compute spectra. There are much more advanced, but it is something that one can dive into real research just by scanning different models and computing the spectra. And you see that transitions here correspond to the band gap. And then there are either stronger absorption or just degeneracy of states that it increases. So we are done. We will start from the skill next time on the next Wednesday. But I promise making such figures will be obligatory part of the projects for everyone. So this is probably the best thing we can do within this course. Okay, meeting is done. Everyone is welcome to disconnect and depart. I will just stay here and answer questions if any.
Thank you.
Stop sharing. Anand has left. Oh, probably he is connected from the cell phone. Okay, I'm finishing the recording.